Hello everyone, my name is Jiangchang, and I'm a PhD student from Nanjing University. Today, I'm excited to share our work, Unveiling Compiler Faults while Attribute-Guided Compilation Space Exploration. This is a joint work with Yibiao, Maolin, and Yuming. Okay, let's dive right in. Compilers play a fundamental role in building system software, whether it is operating system kernel, database system, Android application, or deep learning framework. Almost everything relies on compilers to transform source code into executable programs. However, compilers are prone to bugs. For example, GCC's bug tracker has accumulated over 120,000 reports, and LLVM's issue tracker has more than 18,000 issues. The main reasons are the high complexity of compiler code, the wide range of supported platforms, and the complex optimization algorithms. Bugs in compilers can seriously impact the reliability of the system built upon them, so ensuring compiler quality is crucially important. Traditionally, compiler testing works like this. Diverse test programs are generated using various techniques such as Sysmith, Yibiao, and EMI. Then you take a program, compile it using different optimization levels, and compare the outputs. If the results differ, you might have found a compiler bug. For example, if you compile the source program with GCC, use -0 and get 1 as output. By compiling with -02 gives you 0. That might be a bug. Some methods even refine this by tweaking specific optimization flags, like adding tree loop distribution on top of -02. If the output changes, there might be a bug. But there's a catch. These flags apply to the entire program. What if we want more fine-grained control over how the compiler behaves? That's where attributes come into play. Attributes in C or CVP let you tag specific parts of your code, like functions, variables, or types, to guide the compiler's behavior just for those code elements. Instead of applying settings globally, attributes allow you to fine-tune compilation on a much smaller scale. Here's an example. We have a struct and 2 functions in this program. By applying an attribute to the full function, we can trigger a specific optimization only for that function. Compiling with GCC at -01 then caused a crash, exposing a compiler bug in GCC. What's interesting is that this optimization flag, when used on the command line, would affect the whole program. But as an attribute, it targets just one function. And it's not just optimization flags. Other types of attributes can guide the compiler too. For instance, the no sanitize address attributes on the bar function tells the compiler not to instrument this function with address sanitizer, even if the rest of the program is being sanitized. When GCC compiles this with -02 and address sanitize, it crashes, which reveals a bug. From these examples, we realize that combining attributes with compilation options opens up a much larger space for testing compilers. That inspired us to create our tool, Atlas, Attribute-Guided Compilation Space Exploration. Here's how Atlas works. First, it analyzes the source code to gather information about all the functions, variables, and statements. For functions, Atlas gathers their location in the code, return type, and parameter details. For variables, It records where each variable is declared and what type it is. And for statements, it loads their position as well as any local variables involved. The comprehensive analysis lays the groundwork for inserting attributes later in the process. Next, based on this analysis, Atlas inserts suitable attributes at appropriate locations in the code. These attributes can be applied to different parts of the code, such as function attributes, variable attributes, and even statement attributes, depending on what's most suitable for each situation. Since some attributes only work with particular compiler options, Atlas then selects the right flags for each case. These options can include optimization-related flags, flags that control compiler instrumentation, and debugging flags, among others. Of course, the selection is not limited to just these categories. Atlas picks whatever options are needed to make the inserted attributes work as intended. Finally, it compiles and runs these modified programs to uncover compiler bugs. This is an example of inserting function attributes. After obtaining the location information for functions in the program, Atlas marks all positions where function attributes can be inserted. These are shown as gray in the code. Atlas then randomly selects one or more of these positions for attribute insertion. When adding attributes, Atlas considers both the function's return type and its parameters to choose suitable function attributes. The right side shows the code after insertions, where the newly added function attributes are highlighted in blue. Once the attributes are inserted, Atlas selects appropriate compiler options that compile the program. In this example, compiling with GCC use -01 address stand type triggered a compiler crash, revealing a bug in GCC. This crash only occurs under these specific compiler options. The program does not trigger a crash when other compilation flags are used. As for variable attributes, after obtaining the location information for variable definitions, Atlas marks all positions in the program where variable attributes can be inserted. These are shown as gray in the code. Atlas then randomly selects one or more of these positions for attribute insertion. When adding attributes, Atlas considers the type of each variable to choose suitable variable attributes. The right side of the slide shows the code after insertion, with the newly added variable attributes highlighted in blue. In this case, compiling the program with GCC use the -02 option triggered a compiler crash, revealing a new bug in GCC. This slide presents an example of inserting statement attributes, using a for loop as case endpoint. After obtaining the location information for the for loop, Atlas marks all positions in the program when for loop attributes can be inserted. These are shown as gray in the code. The right side of the slide shows the code after insertion, with the newly added statement attribute highlighted in blue. Atlas does not just blindly insert an attribute. It actually analyzes the relationships among the local variables inside the loop. Based on this analysis, it constructs a suitable sim attribute that fits the specific context of the loop. In this case, compiling the program with clan used the -0 option triggered a compiler crash, revealing a bug in clan. To evaluate Atlas, we focused on three main research questions. How effective is Atlas at finding bugs? How efficient is it? and what unique capabilities does it offer? So, how well does Atlas find bugs? In total, Atlas reported 73 bugs in GCC and LLVM. Out of these, 58 were confirmed by developers, including 1P1 priority or 14P2 priority bugs. This bug affected a wide range of compiler components. We also analyzed which attributes contribute to finding these bugs. It turns out that every single test case involved at least one attribute, and GCC cases actually used more attributes than LLVM cases. On the efficiency side, we ran Atlas alongside other baseline methods for 10 days. These experiments were conducted on the old compiler versions, such as GCC 5 and LLVM 5, and we used creating commit to measure the number of bugs. During this period, we used the test programs generated by C. Smith and Yanjing to evaluate each approach. Atlas ended up finding the most bugs among all the methods. Additionally, over 16% of the test cases generated by Atlas were able to compile successfully, demonstrating the high quality of its test case. The Venn diagram shows the unique bugs found by each method. As you can see, Atlas discovered the largest number of unique bugs among all approaches. Overall, the total number of bugs found by Atlas was 109.1% higher than those found by the other method. We also looked at how quickly each method found bugs. The figure shows that Atlas consistently discovers new bugs at a steady rate over 10 days, without really slowing down. Finally, we looked at code coverage to showcase the capability of Atlas. Under a variety of metrics, Atlas consistently achieved the highest coverage, and the increase in coverage over other methods was the most significant. In summary, our goal is to achieve fine-grained control over the compilation process for more effective compiler testing. To do this, we insert attributes into the code, targeting specific elements like functions, variables, and statements. This allows us precisely influence how each part of the code is compiled. We also combine different compiler options that interact with these attributes, further expanding the variety of compilation strategies we can explore. The key takeaway here is that attributes give us a powerful mechanisms to control with compilation at a very detailed level. This greatly improves our ability to uncover compiler bugs and testing compilers. That's all our work about attribute-guided compilation space exploration. Thank you so much for your attention.